Hello, welcome to our channel for probability and statistics. In this video, we will talk about t-distribution. T-distribution is quite closely related to the sampling distribution of mean. So we know from a normally distributed population and the sampling distribution of the population mean of the sample mean, and the sample size is small and the standard deviation of the population is unknown. In this case, it comes with the student's t-distribution for the sampling mean. Because central limit theorem states that if x bar is the mean of a random sample of size n taken from a population with mean mu and finite variance sigma square, so the limiting form of the distribution x bar divided x bar minus the population mu which we want to estimate and divided by the sigma by the square root of the sample size. So this statistic, say, has the standard normal distribution with mean 0 and standard deviation 1. So just note, in this case, we do not need to say the population is normally distributed or not, because the central limit theorem states that any distribution from the population in the large sample will have standard normal distribution. So where x bar is the sample average, right? But in reality, it is not so perfect with the sample size or under the central limit theory, right? So under the circumstances that n is not very large, or say less than 30, and the population, if the population is normal, but sigma square is unknown. So in this case, we have to use the sample variance as a square in the previous formula to calculate the test statistic. So here we use t to denote the sample average minus the population mean divided by sample standard deviation by the square root of n. Here sample variance as a square equals the mean average of the sample from the sample average, then take a square, then divided by n minus 1. So we transform this t-statistic, go step further, divided by the sigma, which is an unknown population standard deviation by the square root of n, then we can get this t equals to z divided by the square root of v by n minus 1. So here z is same as in the first page we have shown standard normal distribution statistic, and v equals n minus 1 times s square divided by sigma square. So sigma square here we unknown, sigma also unknown, but this term has a chi-square distribution with n minus 1 degrees of freedom. So this t actually is the division of two parts. A standard normal distribution variable divided by the chi-square variable by its degrees of freedom, then take a square root. So this term has t-distribution with n degrees of freedom. And its density function has this form, including the gamma function here. And the t-distribution also has possible value from negative infinite to the positive infinite. So the corollary is from this definition. So if we use the sample average and sample variance, then this term t has a t-distribution with n minus 1 degrees of freedom. So you can see this figure shows several t-distribution density curve. So if we have the degrees of freedom infinitely large, so this is actually the standard normal distribution. So the highest curve, but these two lower curve with degrees of freedom 2 and 5, they have flatter shape than standard normal density curve, because the total area under the curve will be 1, right? So here, for the two degrees of freedom 2 and 5, they has a longer tail but lower or flat top in the shape. And you can also usually use the t-distribution table. So from the left side, different degrees of freedom, and alpha is I'll say the p-value, or say the probability on the right side of t critical value. So here the table lists all the critical value. For example, 1.35 under the 13 degree, then its alpha is 0.1. So here is 1.35, the alpha is 0.1 under the 13 degrees of freedom for a t-distribution. So next we take a look at an example. A chemical engineer claims that the population mean yield of a certain batch processes 500 grams per milliliter of raw material. To check this claim, he samples 25 batches each month. If the computed t-value falls between t0 minus t0.05 and t0.05, he is satisfied with this claim. So what conclusion should he draw from a sample that has mean 518 and standard deviation 40? Assume the distribution of yields to be approximately normal. So here we can say, because we assume the population is approximately normal and the sample size is 25 less than 30, so this is small sample size and with unknown variance from the population. So here conforms the t-distribution case. And we find t0.05 is about 1.711 for 24 degrees of freedom in t-distribution table. Therefore, the engineer can be satisfied with his claim if the sample of 25 batches yield a t-value between minus 1.711 and positive 1.711. So if the mean equals 500, then we calculate this t-statistic equals 2.25 after filling all values in this form. So this value will above 1.711 outside of this range, right? So which means under a t-distribution of 24 degrees of freedom, this population is more likely, or this t-statistic is more likely from a population larger than 500. Because under this degrees of freedom, a t-distribution with value 2.25 will get an alpha value 0.02, much less than 0.05, or say p-value less than the significance error we assumed, right? So in this case, we can say the population is more likely that larger than 500. Or say the engineer will be likely conclude that the process produces a better product than he thought. So because if it is 500, it's very unlikely that we'll get a t-statistic of 2.25, right? Thanks for watching.